So, so welcome everybody to the last colloquium of the year. And today I have the pleasure to introduce to you Michael Tremmel, who is with us from the faraway Midwest parts of the US. And a few words about our speaker. So Michael has been a postdoctoral fellow at Yale University since about 2017, where I first had the pleasure to meet him. But I soon learned that he had an extensive experience working and collaborating with Greeks. So he grew up in Chicago and he did his undergraduate studies at Northwestern University, where he worked with Vicky Kaloyera and Tasso Frago and a few other names that some of you might be familiar. And he did some work on X-ray binary population models. And when he finished his undergraduate studies, he moved to the west part of the US at the University of Washington in Seattle. And he started working on hydrodynamic simulations and galaxy formation. And I think one of the main outcomes of his PhD, if you can correct me if I'm wrong, was the Romulus simulation. And I'm not sure if the name comes from the first Roman emperor, perhaps you can tell us, or the Star Trek reference. And had some amazing work on dealing with simulations of galaxies. And then he continued his work on Yale, where he moved, as I said, in 2017, and work on the coevolution of supermassive black holes and their host galaxies. And I think one of the main goals of your research is also to make predictions for future gravitational waves observations with LISA and pulsar timing array, which I think many people are excited about that. And I think I look forward to hearing more about these things in your talk today, where I think you will talk about insights about supermassive black holes and stuff that we can learn from state-of-the-art simulations. And final thing, I just learned a few minutes ago that you will move to this part of the Atlantic, like the next year. He just got a faculty position in Ireland. So perhaps this will be an excellent opportunity like to meet you in the future or to come and visit us in person. So thanks again, everyone, for joining, and the floor is yours to present.
All right, thank you so much for the kind introduction. And yeah, I'll be moving to University College Cork in Ireland soon, and I look forward to that. Oh no, I think I lost my talk slides. Hold on one second. Okay, sorry about that. Let me. Okay. So hopefully everyone can see my screen now. Sorry, I'm used to having two screens when I present, but I'm currently, actually, as I was saying before, traveling at the moment. So I'm in a hotel. Hopefully the internet stays okay. We don't need to worry about anything. Okay, so today I will be talking about populations of supermassive black holes in galaxies that we don't typically think about. In particular, the two types of black holes kind of in my intro slide here, black holes in low mass dwarf galaxies and black holes that are off center in their galaxies, or what we call wandering supermassive black holes. So the movie playing right now shows a forming galaxy in one of our simulations, and the white points are orbiting black holes. So black holes exist at the centers of galaxies, but they can also exist on a variety of different orbits. So modern simulations, like the ones I'll be talking about, as Jojo said, the Romulus simulations, we can begin to kind of expand our view of supermassive black holes in the universe. And I think it's a very timely thing because this is coinciding with lots of important improvements and advancements in the way we observe supermassive black holes in the universe. Okay, so just a brief overview. Right? We know that supermassive black holes that are millions or billions of times the mass of our sun, exist at the centers of most galaxies, most massive galaxies in particular. We can infer their presence in a variety of ways. One way being looking at the kinematics of stars and inferring, very high mass to light ratios in the centers of galaxies, like the example shown here. So as we zoom in, looking at velocity dispersions of stars, we can infer the invisible mass of a supermassive black hole. We can also infer the presence of black holes through the light they produce as they accrete gas. So as they shine as active galactic nuclei in the centers of galaxies, that process then also lets us know that those black holes exist, and we can even sometimes measure their mass using the spectra of the light that gas emits. This example here is actually of a very high redshift supermassive black hole accreting one of the most massive, earliest and brightest AGN that we know of today. I believe this is like redshift 6 or so. So these black holes are relatively ubiquitous, and what's more interesting is that these black holes seem to be related to their host galaxies. So this is a rather famous plot, the M sigma relation, mass of the black hole relative to the velocity dispersion of their host galaxies, which you can more or less think about as the mass of the galaxies. So bigger galaxies have bigger black holes, smaller galaxies tend to have smaller black holes. And while that maybe doesn't seem too crazy to think about, there's really no reason why the black hole, which is at most the size of a solar system, and 1/1000th the mass of their host galaxy, should know anything about the properties of the galaxy as a whole, or vice versa. So how do these two objects know about each other is really an important question. And what's more is that we understand more and more as we get these interesting observations that these growing black holes can affect their environment. So massive outflows, like in these two cases in observed galaxies, driven by the energy output by these active galactic nuclei, it's likely that they're affecting the evolution of their host galaxies. Not only does the black hole know about their host, but the host galaxy is very likely being affected by the black holes, despite this drastic difference in mass and physical size. And so the question that we try to answer from both observations and theory is, how does this evolution play out over cosmic time? As you go from black holes forming in the very early universe to present day, how do galaxies and black holes grow together? And this is where the challenge lies, because while we're getting really, really good at detecting black holes in the local universe, it becomes harder and harder to fully represent the population of black holes at early times. And how this process plays out really requires theoretical simulations to interpret observations as well. And so for a while now, for the past few decades, simulations have been really useful in trying to understand how supermassive black holes can grow in galaxies and how they can affect their galaxies. And this is in one of the first simulations to really do this in 2005, Tiziano Di Matteo and others, ran a simulation of a galaxy merger with black holes, and they predicted and showed that these mergers can result in black hole growth that then can produce enough energy to quench star formation in their host galaxies. But of course, this is a focus on, because our observations of black holes have typically focused on these more massive galaxies. This is where the focus of these simulations are: massive mergers resulting in giant elliptical galaxies with very massive black holes. Similarly, looking at the most massive galaxies in the universe at the center of galaxy clusters has also been a focus of these types of simulations, looking at the most explosive, most extreme instances of black hole feedback, energy being released by black holes, outflows, jets that are greatly affecting the ability for gas to cool and form stars. Again, in the centers of massive halos, galaxy clusters, where we think that the feedback from black holes is really the most important for regulating gas cooling. And in these now large volume simulations that we run today, simulations which essentially take a uniform cube of the universe, put in a matter distribution of gas and dark matter based on the cosmic microwave background, and then letting that go over time. We have these simulations that produce thousands of these galaxies, all the way from those clusters to more massive elliptical galaxies and everything in between, following the evolution of galaxies and black holes as they grow and evolve, as they go through their individual merger histories, as they simultaneously are affected by internal processes like black hole feedback, star formation feedback, supernova explosions, their environment, merger histories, all of that self-consistently accounted for. And these simulations then produce a bunch of galaxies that we can study, and black holes that we can study and understand how these objects affect each other. Where are the most massive black holes? How are they affecting their galaxies? And we can do things like predict the evolution of these scaling relations, the relationship between the mass of a black hole and the mass of their host galaxies, like this work shown here by Melanie Habuzit, looking at all these different simulations and examining how different assumptions result in different evolutionary tracks of the black hole mass stellar mass relation. How are black holes and galaxies growing over time, and how is this affected by the types of physics that you input into your simulations? But again, even in these large scale simulations that produce many, many galaxies, rather than just individual clusters or galaxy mergers, the focus of black holes is still on the most massive, most extreme events. So the image on the left I'm showing, looking at the most luminous, most massive supermassive black holes at high redshift, and trying to understand the origins of the first bright quasars in the universe. And on the right, I'm showing images from the Horizon AGN simulations, which studied the effect of AGN feedback on galaxy quenching. Again, looking at black hole evolution in the most massive elliptical galaxies, the most extreme events of black hole feedback. And this is all really useful, but it's only part of the overall picture of black holes in the universe. One thing, in fact, that all these simulations agree on is that the majority of black holes in the universe, if you look at the overall population of black holes in these simulations, the majority are lower mass black holes in lower mass galaxies. So on the left, I'm showing again results from the Horizon AGN simulation. On the right is from the original Elusive simulation. And these are basically mass functions for black holes in the simulation at different times. And so across the history of the universe, the lower mass black holes are dominating the population. While maybe it's interesting in certain cases to look at the more extreme, more massive black holes for a variety of reasons, that's only a fraction of the overall population, the overall demographics of black holes in the universe. And what's also in agreement between all these different simulations is that not only are most of the black holes low mass, they're also low luminosity. So if we look at the number density of black holes as a function of redshift across all these different simulations, with different luminosity bins for the black holes, as you go to lower luminosities, especially at lower redshift, after redshift 2 or so, the majority of the supermassive black holes in the universe are not your brightest quasars, are not your most luminous AGN, are not your most explosive feedback events. They're relatively low luminosity, low mass black holes in normal everyday galaxies. But it's still important that we understand how these black holes exist, how they evolve, and where they come from, and what the overall demographics of these black holes are, if we want to have a general understanding of supermassive black holes in the universe. And this is becoming particularly important as we enter into this new era of multi-messenger astrophysics. So gravitational waves, LIGO has already proven that we can see them for stellar mass, lower mass black holes. Pulsar timing arrays are at the cusp of being able to detect supermassive black hole mergers at lower redshift. And LISA, which will launch in 2034 or so, will be able to detect black hole mergers for low mass black holes as low as a few thousand solar masses, all the way out to very high redshift. And so together we're being able now to expand our view of black holes in a way that no longer depends on, only being able to see the biggest, brightest black holes, but our demographic understanding of these black holes is going to explode soon. And we need simulations that are able to more fully understand the overall population of black holes beyond just the most massive, most extreme events in the most massive galaxies. And again, this is only going to be more important as we get better and better observational tools to complement those gravitational wave detections. So Athena, JWST, maybe new X-ray telescopes like LINX in the future, and large-scale surveys like the LSST, which will be done by the Vera Rubin Observatory, will all be able to really expand our ability to detect low luminosity, low mass black holes across cosmic time. So getting, again, a wider view of the demographics of black holes. But all of this, again, requires a theoretical backing to understand and interpret what these observations tell us. And this is where simulations come into play. And in particular, the Romulus simulations, which are the simulations that I've worked on. So Romulus is a suite of 2 simulations. Romulus 25 is a uniform volume simulation of 25 megaparsecs per side. And Romulus C is a zoom-in simulation focusing on a galaxy cluster. So together, these simulations produce, thousands of galaxies. But with high resolution, our focus is on being able to resolve galaxies down to low masses. And we focused a lot on improving the way that we implement black hole physics in the simulations in order to expand the types of black holes we can study. So in particular, we allow black holes to exist in low mass galaxies. We form black holes at early times without any kind of assumptions about which galaxy should or should not host a supermassive black hole. We follow their dynamics self-consistently. So when black holes evolve during mergers, we can predict when they will merge, if they ever merge with their central companion black hole. And we can naturally produce large-scale outflows that can quench star formation in the most massive galaxies as well. So in this talk, I'm going to focus on 2 populations of black holes that we can study using Romulus and taking advantage of the specific way we model black holes in Romulus. In particular, for the first part of the talk, I'm going to focus on black holes in low-mass dwarf galaxies. These are images of a couple of simulated galaxies from higher resolution simulations, zoom-in simulations from Gillian Bellaveri. And then I'm going to talk about off-center black holes that are not at the center of galaxies, but are wandering around on kiloparsec scales or tens of kiloparsec scales. And both of these populations of black holes are typically not what we've thought about historically in simulations, because they've also been the ones that are most difficult to detect observationally. But what I'll argue is that modern observations are getting better and better at detecting these types of black holes. And so we can make some interesting predictions now with simulations that can try to keep up and better understand these new observational data sets. Right. So first part is black holes in dwarf galaxies. The images I'm showing here are different observations of black holes in dwarf galaxies using different wavelengths. So on the left, I believe is detection of a black hole using optical emission lines. In the middle is radio observations. On the right, X-ray observations to find low mass dim black holes, slowly accreting black holes at the centers of low mass galaxies. And this is a relatively new thing that where only over the last, say, decade or so, this population of observed low mass black holes has really taken off. And the importance of these types of observations are, to push our understanding of the relationship between black holes and galaxies down to lower masses. Does the M sigma relation continue on to lower masses in the same way? And this really helps us to better understand this coevolution process, in part because as you get to lower mass galaxies with lower mass black holes, you begin to finally be able to constrain the initial conditions of supermassive black holes. Not only how common they are, where they're forming, right? You're trying to test the extreme limits of how often are low mass galaxies able to actually form these, which can place important constraints on how they can form in the first place. But you're also getting at what their initial mass distribution could be, because these low mass black holes have not grown very much. They haven't gone through as many mergers. They're still more connected to their initial masses. So being able to constrain their initial formation mechanisms is really interesting. But as we also expand our ability to measure the mass of black holes at lower mass galaxies using new techniques, not requiring black holes to exist in giant elliptical galaxies that are quiescent, we also begin to see that these relationships between black holes and galaxies may be more complicated than we previously thought. So in this case, this work by Raines and Voluntari showed maybe that there's multiple relationships between black holes and galaxies, depending on if black holes are still actively growing or if they are more quiescent black holes and quenched more massive galaxies. So all this goes just to say that as we expand our view of black holes, our understanding overall of black hole galaxy coevolution can change a lot. The problem is that in simulations, these low mass black holes and low mass galaxies are basically ignored for the most part. This is a plot showing the occupation fraction, the fraction of galaxies that have black holes as a function of their stellar mass in a bunch of different simulations, large scale cosmological simulations. And no matter what simulation you're looking at, while there are some differences in how they seed black holes, none of the simulations actually have black holes or attempt to predict the existence of black holes in low mass galaxies. So once you get below, 10 to the 9, 10 to the 9.5 in stellar mass, there just aren't any black holes by design, by assumption in these simulations, by nature of how the black holes are put into the galaxies in their chosen models. And so this means that you simply can't test how black holes are co-evolving with dwarf galaxies in these simulations because they don't exist. And this is where Romulus really comes through. So in Romulus, unlike these simulations, we do allow black holes to exist in low mass galaxies. In fact, we make no assumptions as to which galaxies should or should not host black holes. Instead, we form black holes or decide where black holes should exist based on local gas properties. So we pinpoint regions in the early universe where gas is very dense, very metal free, and still relatively cool. So this is meant to approximate regions where a supermassive black hole may be able to form through rapid early growth, regardless of the detailed formation mechanism. All the current favorite formation mechanisms for black holes essentially require low metallicity gas at very high densities to drive the creation of a supermassive black hole at high redshift. So because our formation model focuses just on local properties, we have this evolving occupation fraction over time shown here from Ray Sharma's work actually just a few months ago. You can find it on the archive. And we have non-zero occupation for black holes all the way down to very low masses for galaxies. So we can study black holes in most massive galaxies as well as the smallest dwarfs that we resolve with stellar masses of a few times 10 to the 7 solar masses. So we're really being able to expand our our ideas of how and where black holes are growing. And this is an important difference for how cosmological simulations typically work in this way. So what I'm showing here is the distribution of formation times of the black holes in our simulation, shown in blue. So because we connect to gas properties, all the black holes, which are seeded at 10 to the 6 solar masses in the simulation, are formed within the first billion years or so of the simulation. This is in contrast to many other simulations which seed black holes based on a halo mass threshold. So once a dark matter halo gets above a certain mass, it gets a black hole. But what this would do, shown in the black line, if we were to apply the same criteria to the Romulus simulations, we'd have a prolonged epoch of black hole formation. So black holes wouldn't actually form in a very early universe because no halos are massive enough in this small volume, and instead would form kind of continuously throughout the universe. So when you look at black holes, even if you did have a dwarf galaxy that had a black hole in your based on this formation criteria, the galaxy probably only just got its black hole, cosmically speaking, yesterday, which kind of ignores a lot of the lifetime of that black hole that we know should form in the very early universe. So because we can do this, we can actually track not only the existence of black holes in low mass galaxies, but also their evolution through time, because all these black holes are forming at early times. And so I've worked with lots of people on this, one of whom was Angelo Ricarte, who's now a postdoc at CFA. And he, while he was a grad student at Yale, looked at the relationship between black hole growth and star formation rates in galaxies. And he found this really cool relationship that agrees with observational results from Mullany 2012, where there seems to be an almost constant relation between black hole accretion and star formation in galaxies. This relation holds across all redshifts in the simulation, and basically points to that regardless of the mass of your galaxy, regardless of the of the mass of your black hole, the growth that the black hole has is directly related to how much the galaxy is growing in stars. So galaxies and black holes in our simulation grow together across all the several decades in galaxy mass that we can study black holes. And if we look at the relationship then between the accreted mass, how much mass did the black holes gain over time versus the star formation, the stellar mass, so the integrated black hole growth versus the integrated star formation rate of these galaxies, we find again, a relationship that matches the observed relationships. So these black holes grow together with their galaxies. So naturally, there's a relationship between stellar mass and black hole mass. And this relationship doesn't matter if you're looking in the field, in our volume simulation, or even in galaxy cluster and dense environments. The same relationship holds, because the same relationship between galaxy growth and black hole growth remains the same, regardless of environment. The more gas you have to form stars, the more gas you have to grow your black hole, regardless of galaxy mass and regardless of environment. Now, Ray Sharma, who is actually, I think I went to his defense last week, so he has now officially graduated from Rutgers as a PhD student, but he focused a lot on studying in more detail the dwarf galaxy population in Romulus, looking at the AGN fraction. What are the fraction of low mass galaxies that host an actively growing black hole? So the plot on the left here shows that active fraction as a function of stellar mass relative to various observations. And again, without any assumptions, without any, heavy-handed, criteria for where these black holes should exist and when and where they should grow, we match quite well these observed active fractions for black holes in low mass galaxies. The dashed line here shows the overall occupation fraction of black holes. So one thing you could notice from this plot is that while the active fractions are of order a percent or maybe a fraction of a percent of galaxies, the occupation fraction is more like 10%. So we're missing a lot of galaxies because we simply can't see them because they're not growing fast enough. So what Ray looked at is comparing the X-ray luminosity that we predict from the simulation to the stellar mass and the star formation rate of these dwarf galaxies. And we match remarkably well to the observed population of low mass black holes and low mass galaxies, shown as the X's and crosses here. And the colored points represent black holes in the simulation that we would be able to detect with these modern observational surveys. The grayed out points represent black holes, like I mentioned, that would not be detectable, that are simply not growing enough to be seen in the X-ray in these observational surveys. And so while we match the black holes that we do observe and we match the relationship between stellar mass and the star formation rate, there's a lot of black holes that we simply don't see. There's a lot of invisible black holes in these dwarf galaxies that we predict should exist, that will require better observations to see. Now we can expand our view of black holes in these low mass galaxies by looking in different environments. So the results I just showed from Ray's work is using our uniform volume simulations. You can think of these as field dwarf galaxies. We can also look at low mass galaxies in cluster environments. Now, these galaxies are unique because they're being influenced by their environment more strongly. So ram pressure stripping removes gas from these low mass galaxies and can quench both star formation and black hole growth. And so the black hole population may be quite different in the sense of they may be more invisible than in the local universe. And so indeed, this is the case. If we look at the distribution of Eddington ratios for black holes in these two simulations, in the cluster shown in orange, below, say, around 10 to the 10 solar masses and stars, the vast majority of black holes simply are not growing at all. And that's because these small galaxies are heavily influenced by their environment. All the gas supply that black hole would have has been removed by the dense cluster environment. And so both star formation and black hole activity is shut down. Now, what we have done is predicted what the occupation fraction of these black holes should look like in these different environments. And here we find something very interesting. So despite the fact that these black holes in cluster environments are typically quiet, they're not really detectable, we predict that dwarf galaxies actually have an enhanced population of black holes. The occupation fraction for low mass galaxies is higher in galaxy clusters than in the fields. This is an occupation fraction as a function of stellar mass. In orange is the galaxy cluster simulation, so dwarf galaxies in the cluster environment, and in blue are all the dwarf galaxies in the field environment. And remarkably, the occupation fraction for black holes that we predict in the simulations, again, with a relatively simple formation scheme based on gas properties only, matches very well with nuclear star cluster occupation fractions detected in both Virgo and Fornax. So we have something interesting here, I think, that somehow in the cluster environment produces more black holes in low mass galaxies. And as we try to understand why that's the case, it kind of comes down to the formation history of these galaxies. So it's not so much that anything physically different is happening. That the main important thing to remember is that in a galaxy cluster environment, because these galaxies' growth is shut down at earlier times when it interacts with the cluster environment, the formation time of these galaxies is earlier. And indeed, if we look and compare at how the black hole occupation fraction depends on the formation time, either of stars or of the dark matter halo itself, we see that these environments are not completely different. There is this relationship in the field where galaxies, dwarf galaxies that form earlier are more likely to host a supermassive black hole in the simulation, while galaxies that form later are less likely. The difference is that in the cluster environment, you simply don't have that population of late forming dwarf galaxies. And so you're only looking at the population of these earlier forming dwarfs, which are systematically higher in their occupation fraction. So the population of galaxies and clusters, their evolutionary history is different. And that's why we predict in cluster environments, dwarf galaxies should be more likely to host a supermassive black hole. Unfortunately, because the environmental effects are taking place, they're probably less likely to be detectable through their emission, which is an unfortunate problem. Now, as I mentioned, we can also follow the growth histories of these black holes, right? Because we're not forming the black holes, say, at very late times, but rather in the early universe, we can track the coevolution over long periods of time of the black holes and their host galaxies. And so these are some plots looking at the black hole population in lower mass galaxies as a function of time, their evolutionary tracks showing the accreted mass. So looking at the total integrated growth of the black holes over time relative to the total star formation, the current stellar mass of their galaxies over time. And so black holes and galaxies, as we saw previously, are still growing together at these low masses. The more star formation you have, the more galaxy growth. And so you get these tracks that kind of align like that. But what we can do is we can place the black holes in a few different bins here, those that are overmassive relative to their stellar mass and those that are less massive, or those that have grown more and those that have grown less, and see how does this different growth history affect their host galaxies. Now, this is something that's interesting to look at, because the dwarf galaxies are thought to mostly be affected by environment. This results from Marla Jiha's work in 2012, showing that isolated dwarf galaxies are typically star forming. And only when you get close to a more massive host do you start to see quenched dwarf galaxies show up. But more recent work from some of Marla's students, actually, Jeremy Bradford in 2018, showed that there is this interesting population of gas-depleted isolated dwarf galaxies that also have AGN-like signatures. And indeed, Claire Dickey, another one of Marla's students, looked more closely at these quenched dwarf galaxies, and by looking at spatially resolved spectra, was able to show that as you zoom into the center of these galaxies, you begin to see the presence of an AGN. So while if you look at the total integrated spectra, you might get confused. It might be, whether or not your galaxy is star forming or AGN based on the emission lines. As you zoom into the center, your emission line profile becomes more AGN-like. And so there are AGN signatures in these low mass isolated quenched dwarf galaxies. And so in our simulations, what we can do is look at the cold gas mass as a function of stellar mass, as well as the star formation rate as a function of stellar mass. And indeed, we find that while most dwarf galaxies are star forming, they do have plenty of gas. There are some isolated dwarf galaxies that do lack gas in the same way that observations have, and even more so. And all of these galaxies are hosting a black hole. And the majority of the ones that quench, looking down here, are these red points, which are black holes that have grown more. So dwarf galaxies that have black holes that have had a stronger growth history are more likely to be gas depleted and quenched. Indeed, if we look at what the relative distribution of feedback is like, so the energy from black holes relative to the energy from supernova in feedback in these galaxies, and these red points here point to galaxies where the black hole is dominating the feedback budget. So rather than supernova, it's black hole feedback that's important, which is not what people typically expect in most dwarf galaxies. But in our simulations, among dwarf galaxies that actually host black holes, there is a subpopulation where black hole feedback is the dominant feedback source. And this results in quenching. So if we look at the quenched fraction as a function of stellar mass in Romulus, focusing on the low mass end, overall, about 10% of the galaxies are quenched. But the majority of these quenched galaxies are galaxies hosting black holes. And we look at the quenched fraction for galaxies that don't have a black hole, it's much lower by a factor of several to 10. And so this points to the fact that in our simulations, we're predicting that it is possible to create isolated quenched dwarf galaxies with the presence of AGN feedback. Now, a problem you might notice is that the quench fractions are still much higher than observations, which may point to the fact that we may be having too efficient black hole feedback in these low mass galaxies. Maybe there's too many black holes in these galaxies. I think there's also lots of resolution issues that come into play at these low masses. But what this says is that actually looking at low masses and comparing to observations may in fact be an important tool for constraining AGN feedback, which is again often ignored in these low mass galaxies. So this is the end of that first bit. With Romulus, we can make these new predictions for black holes and dwarf galaxies. We can reproduce plenty of observational results of active galaxies in the low mass end. And we've shown that we predict it's possible for black hole feedback to have an important influence on the evolution of isolated dwarf galaxies, which again may be important for understanding AGN feedback in the future. So now I'm going to move on to the next part. So another type of AGN in these low mass galaxies that has come about more recently is this population of off-center black holes. So Amy Raines did some really great work looking at off-center black holes in low mass dwarf galaxies. And indeed, in simulations, we find these same off-center black holes. So Gillian Bellaveri did some work focusing on high-resolution dwarf galaxy simulations, finding that it's possible to have black holes that are offset from the centers of galaxies, as well as black holes that are offset because they actually exist in really tiny, unresolved galaxies far away from the main galaxy. What else was interesting is that what Gillian found is that the prevalence of these off-center black holes had a lot to do with the dark matter distribution within galaxies. And so on the low mass end, the presence of off-center black holes may have important implications for dark matter physics. And this is something that we've looked into, that I looked into with Ariane Cintio in 2017, and other people have done simulations testing the dynamics of black holes and how they're affected by dark matter profiles, which is really interesting. It may open up a whole new way of testing dark matter. But beyond dwarf galaxies, this population of off-center black holes is actually much bigger than that. So there's this growing body of work showing the presence of off-center AGN sources in more massive galaxies across redshifts. And so it becomes clear that we need to understand what the origin of these off-center black holes are. So this brings me to the next point here, using Romulus to look at off-center black holes, which again, typically aren't thought of because when you're away from the center of galaxies, you're typically not accreting very much, you're not particularly bright, and you're not having a strong feedback effect. And yet this population of black holes, as I'll show, is actually quite prevalent. And so there's a lot of black holes that exist in this state in our simulations. They might be important to understand in the future. So this isn't, the idea of off-center black holes has been around for a while. Semi-analytic modeling and cosmological zoom-in simulations have predicted that depending on how you form your black holes and whether or not you induce kicks from mergers, you could have all sorts of wandering black hole populations in galaxies. But the limitation has often been in how cosmological simulations do the dynamics of black holes. So dynamical friction in these simulations is completely unresolved. In Romulus, we have a model to account for this unresolved dynamical friction, shown here from my 2015 paper. You see applying a correction to the black holes, allowing for more realistic sinking timescales for black holes. So these results here are a black hole orbit in an idealized dark matter halo, starting at 2 kiloparsecs on an eccentric orbit. The black holes in the blue line here are able to realistically sink to the center and stay at the center, while if you don't do anything, black holes remain wandering for longer than you'd expect. But the red line here, I want to point out, is what's typically done in cosmological simulations, especially these large volume simulations with poor resolution. You essentially assume the black hole should always be at the center. So when it's not, you push it there automatically and basically teleport the black hole. So you lose that evolution and you lose that predictive power. But in Romulus, we keep that predictive power because we actually modeled the dynamical evolution in this way. So I looked at the dynamics of black holes and mergers. A main motivation for this is understanding gravitational waves and how often black hole mergers occur. Now, what we found in Romulus is there's two types of mergers that happen. There's this type of merger where the black holes merge relatively quickly after the galaxies merge. And then there's this type of merger where a black hole kind of stays around at kiloparsec separations for quite some time, sometimes billions of years, tens of billions of years in some extreme cases, and sometimes longer than a Hubble time. And so a difference in these examples is that in the top case, you can see a galaxy around the black hole. So it's really the stellar core of this galaxy that remains intact, that's able to bring the two black holes together and dynamically interact with the main galaxy, transferring angular momentum and pushing the black holes, the two stellar cores come together, bringing the black holes along with them. In the bottom case, there is no more galaxy. This black hole essentially looks like it's by itself. Yet the timing of these snapshots that I've taken relative to the merger is the same. So these are very similar mass mergers taking place at similar times, and yet the evolution is very different. And this comes down to the properties of the merger galaxies themselves. So when you have high mass ratio mergers with a secondary galaxy that's more diffuse, that lacks a dense stellar core, you get a very different effect. And to illustrate this, I have a little movie here. So this is a forming galaxy, and there's a little puffy red galaxy down here with a black hole. And as this galaxy interacts with the main forming galaxy, the much more massive galaxy at the center, the galaxy is going to get torn apart by tidal forces. So because you have a diffuse and low mass galaxy, so both of those things, the morphology and the mass matter here, you get tidal forces that essentially rip apart the galaxy, leaving the black hole on its own to orbit on very long time scales. So this black hole will orbit on several tens of kiloparsecs forever, basically. The sinking time scale is just very long at these large separations. And so the result of this is that in our simulations, we predict that more massive galaxies that have these more rich minor mergers in their history have a large population of these wandering black holes. So in this work in 2018, I looked specifically at Milky Way-like galaxies. And these are a few examples of the wandering black holes in this in a few of these galaxies. And overall, on average, or the median number of black holes within 10 kiloparsecs of the center, so within the radius of the disk, more or less, you have roughly 5 or so black holes that are including the central black hole. You have about 5 black holes in these Milky Way mass galaxies within the galaxy, if you will. And this number doesn't really depend on recent merger history or the morphology, because all these black holes were actually put in place at much earlier times. So it doesn't matter if your galaxy is a disk galaxy or an elliptical galaxy or what, the typical number of black holes is roughly 5 or so, not 1. So there are these wandering black holes. And as you get to more massive galaxies, this population becomes richer and richer because you have more and more minor mergers that are getting torn apart by the main galaxy. So Angelo Ricarte, again, he looked at this in more general way in Romulus, showing that this population increases with the halo mass, right? So more massive halos as you get to galaxy groups, that number, rather than 5 to 10, becomes more like a few hundred wandering black holes, up to a few thousand if you look at galaxy cluster environments. So this population of wanderers becomes very rich at higher masses. And if you consider the mass budget of black holes, so the total accreted mass budget in the universe of black holes, at late times, not surprisingly, central black holes are the most important, right? They're the ones that are able to accumulate the most mass because they're the center of galaxies. They have the most gas supply. So the total accreted mass budget in the universe, and as a function of halo mass, these central black holes shown in black here dominate. As you get to higher redshift, these colored points and the black points begin to be more mixed up. So these off-center black holes in these galaxies are also important, right? The central black holes haven't yet had a chance to grow as much. And at higher redshift, you have a lot more wanderers because the black holes haven't had a chance to actually sink to the center yet. So understanding off-center black holes may be also really important for understanding what the total mass budget of black holes in the universe is, especially at high redshift. But now the question becomes, okay, our simulations predict these wandering off-center black holes. Can we actually see them? And I think that one thing we've looked at is it is oftentimes possible that these black holes do become luminous enough to detect. So Angelo, again, in his 2021 paper, looked at the population of these wanderers and what their X-ray luminosities would be. And the majority of these black holes are not growing very much. But every so often, especially these more massive galaxies like the one shown here, where you have more of these black holes, it becomes more likely that at least a few of them encounter some gas and are able to grow even at a low level. In this case, we marked the black holes with bolometric luminosities greater than 10 to the 42 ergs per second. So it's low luminosity, but still at low redshift, at least detectable. And indeed, if we look at the spatial distribution of these bright black holes, we match quite well with some recent results looking at hyperluminous X-ray sources. So looking at X-ray sources with bolometric luminosity greater than 10 to the 42 ergs per second, the spatial distribution predicted in Romulus, the overall distribution shown in red on the bottom plot, matches quite well with the Barros et al. Result for these hyperluminous X-ray sources. So these point sources that are luminous offset may actually be low luminosity supermassive black holes, or at least it would be consistent with observations to think of them in that way. Now, one thing we could do in the future is stack our galaxy results to try to find the overall X-ray contribution from these wandering black holes. And we've done this with Romulus, and we can predict that there is kind of this sweet spot mass range between 10 to the 11 and 10 to the 13 solar mass halos. So bracketing roughly Milky Way mass galaxies, where these black holes are luminous enough to be detected above the emission from X-ray binaries and hot gas in the host galaxies. So yeah, this sweep, as you get to lower masses, there's just not enough wanderers and they're too dim. As you get to higher masses, the wanderer population is actually less active because there's less cold gas, because the halo masses are higher, the virial temperature is higher. There's a few other ways that we've explored to detect these black holes. I'll move quickly because I know I'm running out of time, but looking at the gravitational lensing influence of these black holes is difficult. We did some work using these thinly lensed arcs. If we could potentially detect the presence of wandering black holes in the universe, perturbing these thin arcs of lensed galaxies. But we need about 10,000 of these to observe one wandering black hole. At least that's what Romulus would predict. Another interesting possibility is actually looking at our own galaxy with stellar streams and these interesting breaks in the streams that is due to some compact, dense, massive object, which could be a wandering black hole of mass above 10 to the 5 solar masses. As of right now, there's no globular cluster that exists that can explain some of these breaks that we see in these stellar streams that Gaia has seen more recently. And then there have been really nice observations of ultra compact dwarf galaxies. So these are the dwarf galaxies after the galaxy has been all stripped away, hosting a more massive black hole in the stellar core of a once more massive galaxy in these galaxy group environments. So Anil Seth and Karina Vogel have done some really great work trying to find these black holes. And this is exactly the type of thing that Romulus is predicting. We just can't resolve these compact dwarf galaxies that still exist around the black holes. But this is all pointing to this new era where we're seeing black holes in more unique situations, not just at the centers of massive galaxies. And so the overall summary, right, we can predict wandering black holes in Romulus because we have good black hole dynamics. We predict that they may be detectable. We may have already detected them with hyperluminous X-ray sources. And there's potential in the future for more work detecting them from their luminosity, even though they're low luminosity overall. And yeah, so I'll leave up this quick summary slide and I'll take your questions. It's hard for me. Hopefully I'm still roughly on time because of our later start. But thanks a lot for listening to me talk.
Yes, we are perfectly on time. So thank you very much for this excellent presentation. I think you covered many interesting topics. And I think none of us in the audience is an expert in galaxy formation and evolution, so probably our questions are going to be easy for you to answer. So let's open the floor now to questions. You can unmute yourselves and ask our speaker your question. I see Marcos has a question. Yes, please go ahead. We cannot hear you. Yeah.
No, I presume. No.
Yeah, we can hear. I think I can hear. There's some background noise, but I think you're good.
Now?
Yeah.
Okay.
We can hear you, but with some background noise. Maybe you can reduce a little bit.
Now it's too low.
No, you're good.
Now?
Okay, now it's good. Now it's good.
Okay, sorry for that. So I'm really interested into black holes in general. I just started my PhD in San Sebastian with Silvia Bonoli. and I'm doing some analytics, and I'm somewhat familiar with many of the topics referenced. So I would like to ask, in particular, about the seed mass used in your simulations. So it's always 10 to the 6th, right?
Yeah. That was in part a choice made because of the dynamics. We need a more massive black hole to resolve the dynamical evolution. But yeah.
So one of my colleagues, Daniel Espinosa, has worked his whole PhD on seeding, and he has found out that light seedings are more abundant than 10 to the 4 and 10 to the 5 solar masses black holes. So I would like to have your take on that, like how this would affect black hole occupation and all these wandering black holes that are produced.
Yeah, that's a really good question. Yeah, it's unfortunately a necessary evil at this point. I mean, yeah, the seeds we have are more massive than we'd expect from formation schemes. I think that the greatest effect would be, again, because we're not making any direct assumptions about like what kind of formation mechanism is in place. It's purely just, picking out these gaseous environments in the early universe. I think the biggest effect this will have is potentially on the luminosity and on the feedback of these black holes. So it could be that because these black holes are more massive than they could be, maybe a 10 to the 6 black hole is really a 10 to the 4, that would really decrease its accretion rate, and you'd be less likely to see it. In addition, it could come back to this idea, I think I'm showing the slide right now, that we do have too many quenched dwarf galaxies, and that's mostly due to black holes. So if we think that our occupation is okay, it might be that because the black holes are more massive, they're producing more growth and more feedback than they normally would. That said, the complicated thing that we've found is that it seems like the black hole mass is less of a predictor for accretion rate than the star formation rate. The most important predictor for how fast a black hole is growing in a galaxy is actually how much gas is around. So it seems to be more supply limited in the simulation. So it's unclear exactly what an effect it would be, but I could definitely see having a population of much lower mass initial black holes may be much less efficient at growing, just because they're less massive, and also because they could be more likely kicked around the galaxy and removed from the center. So it's definitely possible that this is kind of how to put it, that our simulations are a bit optimistic in the amount of growth that these black holes go through at the low mass end in particular. So unfortunately, we need high resolution to do some lower mass seeding tests. But yeah.
Okay, and a follow-up, not related, regarding observations. So there are some couple of papers coming out in archive these days. One from Polymer, I don't know if you're aware, regarding emission lines and this new class of star-forming AGN dwarf galaxies. And they seem to have improved like the percentage to like 10 and 13% of AGN fraction in the whole population of dwarf galaxies. Is this consistent with Romulus? Would you like to be more? I mean, what's regarding observations, what would be needed more to unveil all these wandering black holes?
Yeah, so the dwarf galaxy black holes that you're talking about, I do think that those results are relatively consistent with Romulus. So we have an occupation fraction of roughly 10 to 20% for low mass galaxies overall. But again, we predict that the relative to these surveys that already exist, which really just have a luminosity threshold for X-rays, that they wouldn't be detected in these X-ray surveys, but these more careful emission line studies are able to bring them out. And so unfortunately, it's more complex. So one challenge that we have in simulations is translating the accretion rates that we have in the simulation to observational, directly observable characteristics. So X-ray luminosity is sort of easy because we can apply bolometric corrections, and people have studied this in detail, but producing emission line spectra is more complex because it's not directly always related to just the accretion rate itself. It's also the status of the gas that we don't resolve nearby the black hole. But overall, I think that higher occupation fractions and having these black holes that were previously invisible come out is definitely consistent, because as I mentioned, there's our simulations predict that the majority of black holes in these lower masses wouldn't be detected in your typical X-ray survey. So I saw that paper, and it's actually really cool. I haven't had time to put it in the talk yet though, but I definitely should add it in there. But yeah, I think it's very exciting stuff that I would say is consistent.
And since I have the microphone, one last question. I would like George answer his own. Regarding the X-ray luminosity function and the bolometric luminosity function in general. So your simulation fits in different redshifts the bolometric luminosity function, because as I'm aware, most of the simulations overpredict at low masses the number of AGN, and semi-analytic models too is something that we are trying to really hard to figure out. So
yeah. So we have a really small volume, so it's hard to. We don't have enough to test on the higher luminosity end of these luminosity functions. Our most typical black hole has luminosities like 10 to the 43 ergs per second, and only a handful have like high luminosities. But I will say, yes, I do think that we overpredict the low luminosity, much like these other simulations. But I'll also say that again, this comes back to the challenge of taking simulation data and translating it to observational data, because there's lots of uncertainties about bolometric corrections for one, but also obscuration and things like that. And so it can be quite difficult. And yeah, I'll just leave it at that. But I do think we have this we have the same problems as the other simulations.
Okay.
I don't think that we're unique,
because if you didn't, I would be, we'll take the
oh yeah. Yeah, I would say we have the same problems, but again, a lot of it is massaging the data, as lots of people do, and that's not great. So all I can say is we do. I'm not sure why. There's lots of different ways to kind of explain it away, but
okay, thank you.
Yeah.
Yeah, I think that Marco's question sort of beat me to the punch. I was about to ask something about that, because on your first part of your talk, you talked about the luminosity function and the correction for the high intensity or the low intensity with that function that was used, I think on slide 25 or 26. And okay, I understand that this can like qualitatively explain the observations in some way, but like, if you change that function, like that low and high intensity part, like, is there actually a test that you do that you say, I prefer this luminosity, this bolometric correction from the other for different luminosity levels? And like, I think the answer lies into the faint sources, what's happening there. So it goes like, sort of like a second part of my question, like, Chandra is sort of dying, and you're looking at all these systems with Chandra, and the effective area of Chandra is going down. So you are going to need the next generation of X-ray observatories to find these systems. And I'm not sure what's next there. Like Lynx is not certain. There are all these evolution, all these things happening with Athena, for example, that the scope of the mission might completely change and go into the late 2030s. So is there something like that you would like to see in terms of observations in the next, let's say, 10 to 15 years to come along and help to solve this problem? Or what would be the smoking gun to help you constrain that function, like the bolometric? Sorry, it was a long question.
Right. Yeah, I mean, I think that's a really good question. I think that at 0th order, the first thing is we need to be better at detecting black holes at lower luminosity in the first place. And moving away from flux limited things. So for example, there's some really interesting work. I mean, Vivian Baldassare, she was at Yale, now she's at Washington State. She has this really nice method of detecting black holes that has to do with variability. And so big surveys like actually LSST done by Vera Rubin could potentially, because it has good time cadence, could actually bring out some of these variabilities in optical light that aren't necessarily luminosity limited, but will point to the presence of a black hole in more complete fashion for these lower mass black holes. So you wouldn't be limited to black holes that are very, very bright, but instead black holes that are bright enough to produce this kind of variable signature in these optical wavelengths, which I think could be a really interesting way to expand and make a more complete sample of black holes and dwarfs. So I think the problem is right now that we have no way of understanding what the completeness kind of is in terms of how many black holes we think exist in dwarf galaxies. And so, yeah, I think the first step is being able to find them more completely. And so we can do a more in-depth analysis. But other than that, like it's hard. The bolometric correction thing is difficult because, again, right now that's all been based off of black holes that are 10 to the 43 or 10 to the 42 ergs per second or more luminous than the X-rays, because those are the ones that we see the most and can actually do that analysis for. So I guess having more low luminosity black holes where we can also measure the masses, which is another thing, right? Being able to use these new techniques like reverberation mapping and things like that to actually infer the mass of the black holes in these galaxies simultaneously with their luminosities and all that. That I think is where it's going. And I think that there is, because of work like Vivian's, I think there is a chance that we can get a more complete demographic population of these dwarf black holes and explore in more detail these lower luminosities. But yeah, I guess there's also the additional problem, not only of bolometric corrections, but also of obscuration and all of that. And that's a whole other can of worms that, again, is very difficult. And yeah, I'm honestly not positive what the best way forward in that sense is. I think there's lots of interesting work coming out looking at, using like X-ray, like Meg Urry's group, for example, has been looking at X-ray surveys and trying to look at obscuration things using modeling and things like that. From I think there's actually lots of work from the simulation side to do there. So as simulations get more detailed, higher resolution, we can actually make our own predictions for what the column densities are of these different things and actually help in the opposite direction. So yeah, I know that probably doesn't really answer your question, but I think there's potential things. I don't really have any good answer for like. Yeah, bolometric corrections are tough.
Yeah. Can I ask something, follow up on the one of your last slides that you went a little bit? It was one that you mentioned Karina's work on the dwarf galaxies. And this work was based on like HST data, right? So do you expect like a new breakthrough on this kind of sources with James Webb or like future observations finding more of these systems?
Good question. I am not an expert enough to on the observational side of this. I don't know if I can come up with a good answer for that. I think that maybe a short answer is yes. I think that the main limitation is having the detailed spatial resolve spectra to do this analysis. I think that when you mentioned JWST, I think actually the best thing there, JWST's strength is going to be more at high redshift, I think, for the black holes. So for these, I think I think it's more about finding them in the first place. So like, I think a lot of the challenge is actually like finding the things to look at,
Yeah, I think that was mostly what I was thinking. Like, are they, can we find them often in lab that we will just find them by random in observations with better telescopes, or do we really have to have a plan to dig them out?
Yeah. I think anything that will allow us to detect lower mass galaxies better is going to be the key here, right? Because first you need to actually see these ultra compact dwarf candidates, and I think that's kind of where things start. Is you have an ultra compact dwarf and you do the analysis to find the black hole. These black holes aren't active for the. I don't think in any case they're particularly active. So it really comes down to actually being able to find the the compact dwarf, which you can imagine at small separations like the one I'm showing on the right here is really hard to do. But actually, even in current generation, this has been something. So this is how people are looking for dual AGN a lot, is systems that have multiple, what they call multiple bulges or multiple cores. So you can actually find, these multi-peaked systems of galaxies that look like they're kind of merger remnants, and things like that I think can totally be done and will be improved by more sensitive telescopes. I'm not exactly sure specifically for JWST or anything, but as we get down to lower magnitude limits in terms of galaxies, it's all going to help, I think.
Okay, thanks.
Yeah, sorry for my long-winded answers.
No,
I understand it's a complicated issue, so it's nice not to have like yes or no quick questions. So it's room for further improvement.
So are there any questions from the audience? May I ask one? I saw also Apostolos Mastichadis would like to ask just one quick question. I didn't, maybe you have mentioned it, but I didn't quite understand it. I was wondering, you described this, that you start in your simulations with these seed black holes of 1 million solar masses, and then you see them grow, both because of accretion of gas in the galaxy, but also because of mergers between galaxies. And I was wondering if you have like, what is the relative importance of mergers versus gas accretion that determines the final mass of the central black hole?
That's a really good question, and we're looking more deeply into that right now. That's actually something we're working on at the moment. I would say just in general, once you get to more than say 10 times the seed mass, the seed mass becomes less important. So the growth overall is accretion. Now, the tricky thing is when I say accretion, I mean like mass that's not related to the seed. So you can imagine black holes where they're 2 or 3 times 10 to the 6 solar masses solely because of mergers. And so mergers are purely dominating. Well, there's other black holes that have mergers, and that those mergers bring in black holes that have grown different amounts. But if you look at overall the accretion, the total accretion history of all the black holes all put together, the accreted mass dominates over the sum of all the initial masses, if that makes sense. So it's kind of complicated, because you could also say that mergers are important because they're bringing in gas black holes that have accreted a certain amount of mass. And that's kind of where we're at right now, is trying to understand what's the balance there. But in terms of connection to the seed mass, once you get above 10 to the 7 or so, there's less, you're less sensitive to the seed mass. So if I were to take those black holes, I were to take away all the mass of the seeds, and see what the mass was, it wouldn't change dramatically once you get above that point. But below 10 to the 7, you get a more variety, and there's some black holes that are very sensitive. Their masses are very much tied to their seed mass. So that's the best answer I can give right now. But I think that is definitely a question we're thinking a lot about. Yeah.
And if I may ask one more.
Yeah.
Yes, so I was wondering about the accretion onto the black holes. And I saw in one of your plots, like the Eddington ratio, I think it was like going from 10 to the minus 3 up to 10 to the minus 1, if I remember correctly. And because I'm not a simulator by no means of galaxies, I was wondering, what determines, I suppose that you put like a hard upper limit in the accretion rate, or is it something that it is self-regulated? And is it possible to go to super Eddington accretion rates into some cases for the black holes?
That's a really good question. I should clarify that. So in the simulation, we do assume Eddington limited growth. So we assume a radiative efficiency of 10% and apply the Eddington limit. So we basically take the minimum of the accretion rate that we predict just from looking at gas density and the mass of the black hole and the Eddington limit. So we cap it at 1. But for the most part, the black holes are growing at significantly less than 1 in terms of the Eddington ratio. So it's very rare that we get black holes that sustain accretion near Eddington in the simulation. That could just be a result of the fact that we have a small volume, and so we're not getting those really big black holes and the really big galaxies. But yeah, for the most part, the Eddington limit does not drastically affect the growth, but we do not allow super Eddington in the simulation. So
okay. Yes, I will stop for now, and if we have time, I might ask one more. So just to give room to the other people to ask questions.
Yeah, okay. Might have. Thank you very much, Mike, for your talk.
Yeah.
I would like to continue from where Maria, there's more or less a similar question about the Eddington luminosity. First of all, do you consider that you might not have Eddington at all, you might have ADAF systems, for example? And our galaxy, for example, there's so much gas in the center, so much gas around, and still you don't see but a tiny fraction of it. Therefore, I'm not sure how many of these black holes are could be Eddington dominated, or there could be something like an ADAF. One thing is this, and the other is, in your simulation, what makes an AGN? When you say, I mean, this is a very basic question, but I didn't understand it. Because you talked about AGN activity, what are you talking about? Observations, or you have some criterion that you say, oh, okay, now we have an AGN. This is related to the previous.
No, both of those are really good questions. And I think, let's see. Oh, come on. Let me bring up one slide in particular. Right. The definition of what is an AGN or not, I think that's a really good question. And that's honestly a huge headache for me as a simulator, because it really depends on what observations you're comparing to. So in this case, what I'm showing here on the slides are, our definition of AGN here is, would it be detectable in these specific surveys with a certain X-ray flux limit, and comparing to requiring that the X-ray luminosity be greater than the X-ray luminosity of the galaxy, hot gas, and X-ray binaries and all that stuff. So typically, our definition of AGN is something along those lines. You'll have an observational survey you're comparing to, and you require a certain luminosity from your black hole, with a certain assumption about radiative efficiency and bolometric correction and all that. But given an X-ray luminosity that you can assign a black hole, would it be detectable in these surveys? An X-ray luminosity is what I say here because that's kind of the easiest. The complicating thing is that when observers say something is an AGN, it really is just, are we able to see it as an AGN? And every observational survey has different requirements for what that means. And so things like emission lines, you're using like the BPT diagram, things like that to determine the presence of a black hole. That's really hard for simulators to approximate. So it becomes really hard to compare directly to those types of surveys. So typically our AGN are more like a flux limited thing, growing above a certain rate relative to their host galaxies. And I'm happy that you brought up, why can't I go back here? There we go. I'm glad you brought up this idea of advection dominated accretion flows, because this is another thing that we found. So when we do the simulation itself, we assume that the radiative efficiency is a fixed number of 10%. So 10% of the mass energy that goes onto the black hole is re-emitted as energy, as light. If we were to use that number, we would get actually a lot more AGN predicted in the simulation. But instead, we found that if we assume that at low Eddington ratio, that radiative efficiency actually decreases, shown in this equation here, and this is done not only in this correction is something that's been done I should have had the citations on here, but there's a few different papers that use this same correction. So the low Eddington ratio black holes, if we assume that they accrete less efficient or they radiate less efficiently, then we are able to actually predict similar occupation fraction, EGN fractions as observations. And so this is another complicating factor, right? Because all this extra physics is something that we need to put into the model when we're comparing to observations, but also this isn't perfectly self-consistent because this isn't the radiative efficiency that we assume in the simulations themselves. And so it's challenging. I think there is evidence that, and other people have shown in observations that there's evidence that black holes are not as luminous as we'd expect them to be for a given accretion rate. And these accretion dominated flows, as you get to the low Eddington ratio, even the bolometric correction, as Giorgio has mentioned, is also really hard. So it's just I would say it's a mess. It's hard. This is the best we can do. I think we do see evidence that we need some kind of low radiative efficiency for these tiny black holes. But again, it's all assumptions that we put in. And when we get out something that matches observations, we can say, all right, we did it. It doesn't mean it's necessarily the right answer. But yeah, I know that, again, my long-winded answers here, but I think that it's definitely an issue and no one really has a good solution because our accretion models are relatively simple because we don't resolve the detailed physics that determine whether or not you have ADAF or not. So that's kind of where we're at, right? We're using Bondi accretion still, right? So it's hard to really say.
Thank you.
Yeah.
Yep.
Would you like, sorry, please go ahead. No, I can ask one more. So at the beginning of your talk, when you were describing the Romulus simulations, you mentioned that you naturally produce the outflows, right, for creating the feedback. So how is this taking place in your simulation? How do you define or create when the outflow will be produced?
That's a really good question and kind of relates back to this this radiative efficiency issue, right? So what we do in the simulations is just assume that some fraction of the emitted energy, so each black hole is accreting at a certain rate, 10% of that mass energy we assume is being radiated away, and another fraction of that energy is being coupled to gas around the black hole. So we assume that 2% of that energy is coupled thermally to gas nearby the black hole. So we then increase the thermal energy of the gas nearby. We basically just pump in a bunch of energy, and that gas naturally becomes very hot and buoyant and produces large scale outflows. Every black hole in this case is treated the same. And when I say it wasn't a huge point of the talk, so I probably shouldn't have used the language I did. But when I say naturally, I'm really comparing to some other. So
yes, to other simulations.
Yeah, this idea of needing outflows is really important, and people have different methods of doing it. And so we make as few assumptions as possible, do the simplest thing possible, put in the same fraction of energy for every black hole into just the thermal heat of every gas particle and let things happen, and we produce outflows. Other simulations, when I say unnaturally, maybe what I mean is they put in the outflows by hand. So they give gas and kinetic energy in certain directions and produce those outflows and say, okay, gas on these scales is moving with this velocity. And oftentimes there's a give and take there, because, for example, in TNG, illustrious TNG, which is another one of these big simulations, the assumption there is that there's two modes of feedback. There's this thermal feedback that we do, and there's this kinetic feedback, which is probably true. There's this radio feedback that takes place, and the nature of how you're transferring energy, is it kinetic versus thermal, is a big question. And so the assumption is that more massive black holes with low Eddington accretion rates are producing different feedback, and that different feedback is actually critical to quenching galaxies, which I think is a legitimate argument. It does mean that some of those assumptions are, so that is a double-edged sword. Doing something that's more complex could give you better results, but at the same time, it means that the assumptions you've put in are more likely to be,
Yeah,
you get out what you put in. Yeah.
Yes, exactly. You have more freedom in a sense because you add more assumptions and you add more elements into the simulation. Yes, but I just wanted to understand how exactly is the outflow produced here, and it is thermally driven, basically. Okay.
Yeah.
Okay, so that's all from my end. I think that we kept you like half an hour questions.
Oh, I appreciate it. I'm glad there was questions. Thanks for.
We exited the conference room. Now we're in the coffee
The lounge
room outside.
Exactly right. Yeah.
So I will stop recording then.